Let's continue our study of searching by improving our list-making software. The original problem statement was we created a list-making program. It keeps track of a persistent list. Now, what I mean by persistent is the data in the list is remembered between different executions of the program. So you can put some things in the list, then you save it to a file, and when you open the program, it reads from that file. Remember that we retrieved data to and from a file, and we added and removed items and showed the list. Here are the new features. A feature that I found to be very useful is one that was inspired by workflowy.com. What they do with their list-making software, amongst other clever, amazing things, is they have hashtags on individual items. So, for example, you could say hashtag shopping or hashtag to do, and then you can do search on those. So you could pull up the things that are just on your shopping list or just on your to-do list. Surprisingly handy. We also haven't done any reordering of list items, like moving items up and down, or more general reordering, taking the 6th item and moving it into the 2nd space. These are features that are well within our grasp at this point, so let's add them in. Now here's our strategy. We're adding in 3 separate features. What we want to do is work on them one at a time. And I recommend that you work on the easiest one to the hardest in a case like this, because the things that you learn doing the easy ones will make the harder cases easier. Now, different people like different strategies, and this is just my recommendation. There's no hard and fast rule that this is the way it absolutely must be done. So, in my opinion, the easiest feature is moving up and down. In fact, you're going to be surprised how easy it is to implement that feature. Moving to a given position, our more general reordering, that's going to be the 2nd easiest feature, and the hashtags are the 3rd easiest feature. So that's the order in which I'm going to work through things. Working in these small separate iterations is really a good idea. One place where people get lost in programming is they try to do too much at once, and then they end up with 3 things that are half finished instead of having one thing that's actually finished. So this is a strategy I recommend that you adopt. And of course, we'll want to test all the features after each feature is added. And when I say test all the features, I mean you have to test the ones you previously developed too, because it is possible to break other things while you're adding in new things. So this is a very important part of testing. Now, I've written the user interface in advance and written some of the signatures for the methods just to help us move along a little bit and get to the interesting part of the coding. The first thing we do, as always, is design our test data for move. So, of course, we're going to run all the original tests again. That's very important to know that we didn't break other things while we were doing move. Now, for moving up and down, we could do something like put A, B, C, D, E in a list. Then we could move E to the front 1 position at a time, and then move E to the end 1 position at a time. If you think about it, that will test all of the possible cases that exist. So that's a pretty easy way to test the software. You'll recall that when we designed the original program, we had some similar methods. So we had a method called add item to list, and it took an array list and a scanner as parameters, and we had delete item from list, and it also took an array list and a scanner as parameters. We definitely want to keep our design consistent. So in both of these cases, the user did the data entry inside the method. Now, that isn't the only way this program could be written. And in fact, a lot of people would tell you this program should be written with the user data entry outside of the methods. But it is the way we did it previously, and so we want to be consistent with that. We don't want to end up doing it half of one way and half of the other way, because then when we have to go back and change this program again, it'll be hard to do. Here's what the signatures should look like. Now, you'll see I've got 2 different design possibilities here. One has a method called move up and another has a method called move down. So those would be one choice. Or we could create one move method and pass in a Boolean that would be go up, which would be true when we're going up or false when we're going down. Now, both of these are legitimate designs that could be correctly implemented. I've picked design number 1 as the one we're going to implement. My reasoning behind this is because we're doing data entry inside the methods, it makes a little more sense to separate move up and move down. It makes a little bit cleaner code. But if you chose the other way, it could be fine too. And in fact, you might want to implement the other way. Let's think about how we're going to implement moving up and down. So suppose we have a list that contains A, B, C, D, E, and we move B up one position. Well, then we have B, A, C, D, E. The C, D, E remain the same, but the A and B swap. Well, that's a swap operation. And as it turns out, if you think back, the collections class did have a swap method. Now, we haven't used it before, but that doesn't mean we can't use it now. Here's what the signature looked like. It returns a void. The name of the method is swap, and it takes a list parameter. Remember, it's okay to pass an array list to any list parameter. It's also okay to pass them into collections. And then you have int I and int j, and those are the two indices that you want to swap. Remember the list of question mark? That's just some crazy syntax that we don't understand just yet. So don't worry about that question mark too much. If it's a list, things are going to be okay as long as you're doing things that make sense. So let's go and implement our method. So here we are back in Eclipse. You'll notice that I've renamed the class to ListMaker with hashtags. Also, as we look at our import statements, we see that the collections class has not been imported yet. So let's do that. That's java.util.collections. Of course, Eclipse is complaining that we haven't used it, but we know we're going to. You'll notice that I went and added a bunch of constants for all the different possibilities in our class. Here's our main program. So it's got a while loop where it's going through the choices. Then remember, you select from a menu. That was a method that we wrote. And then you go through the choices one at a time. So add, delete, show, move up, move down, move to position, so on and so forth. The last thing we do is write the file to the list. Basically, I just added in parallel structures for our new methods. Here's our move down method. Now, I've printed out to the user which item would you like to move down, and then we get the input from the keyboard. Remember that this will be unit indexed because that's how the user is going to think about the list. So when we check the range, we really want to think about how we want to do that. So what I recommend you do is do index equals index minus 1. So we change back to 0 indexing. And notice that I'm making comments on these things. The reason I do that is because we might have to maintain this software someday, and things like that look wrong if you don't realize why they're there. So you don't have to put a comment on every line, but sometimes it really helps. So now when we check the range, well, if you think about it, when you're going to move things down on the list, your possibilities are actually 0 to the size minus 1 element. Well, now wait a minute. Is it really size minus 1? Because if we choose the last element on the list and ask to move it down, that doesn't make sense. Now, in this case, I would beg for some compassion for the users. If they tell you to move the last item down, just ignore it. Just don't do anything. Because that's a case that doesn't make any sense, and there's no reason to give them some big elaborate error message and force them to remove things. They probably know they typed in the wrong number, so just don't make a big deal out of it. So here's the range. If index is greater than or equal to 0, and index is less than or equal to list.size. Let's think through these very, very carefully. Moving down, index 0 certainly makes sense because it can go to index 1 or index 2. Moving down at index.size does not, because remember, the last item in the list is size minus 1. So when we put it this way, size minus 1 would be acceptable. But actually, we probably want to stop a little bit sooner than this, because remember, it doesn't make sense to move that last item down. Now, there are lots of different ways to deal with this problem, but here is one possibility. If index equals list.size minus 1, return. So that way, if they ask you to move down something that it doesn't make sense to move down, you just don't do anything. I think that makes pretty good sense. Now we can see if index is greater than 0 and index is less than size minus 1. If that's true, well, that's when we want to be doing our move. So let's move our little comment up here, perform the move, and we decided we were going to use collections.swap, and we're going to swap in the list. So the index is the first position and we want to move it down. So we're going to swap index and index plus 1. Now this gives us another chance to think about whether we're doing the right thing with the indices here. So let's think about what would happen if we pass in index of list.size minus 2. Now that's going to be the largest number that's going to get inside this if statement successfully. Well, at that point we'd be swapping list size minus 2 and list size minus 1, which is in fact the last two elements. So that looks like we're doing the right things too. Now in this case, I'm not giving the user any feedback on errors they make. They would just be able to call the functions again. That's kind of a lean, mean way, but it's also not as annoying for the users as being constantly prompted for errors that they're making. Okay, now because these are so short, let's do move up at the same time. Of course, we always could do the testing. We've got a pretty good idea here. So let's copy this code. But of course, we want to think through the code one line at a time. So first we change back to 0 indexing. Now, when we're moving up, the case we need to worry about is the index being 0. So if it's 0, we just return because it doesn't make sense to try to move up the first one. Now, if index is greater than 0 and index is less than size, so notice we've got a whole bunch of little off by 1 things we have to pay attention to. Then we swap index and index plus 1. Well, those aren't the right ones because that would move it down. We want to swap index and index minus 1. Now, because we have a minus 1 in there, we want to make sure that doesn't go out of range on our array list. So the smallest index we can pass in is 1, because we tested to see if index was greater than 0. What that means is the two indices we'd be swapping are 1 and 0, and those are in fact the correct indices. So let's get rid of that extraneous comment, and that looks good. We're now ready to test our software. So the first thing I'm going to do is add some items. I'm going to add A. Then we're going to add another item. And we're going to add another item. Add another item. Add another item. And now we want to show our list. Because our user interface is taking up more space now, we need a little more space to run our program. So we have A, B, C, D, E, and then A. Did we add A in twice? That looks a little suspicious. So let's see, go back and see what we did. So we entered A after item 0, then we entered B after item 1, C after item 2, D after item 3, and E after item 4. So I wonder where that extra A is coming from. Now, we haven't actually used our moving program yet, so we might think about some possibilities of what could have gone wrong. I'm going to spare us a little bit of debugging time here, because what's really going wrong is, if you'll remember, we wrote out our data to a file. And since we've written out our data to a file, we have leftover data hanging around. In other words, we didn't clear our list when we started. Now, we really should have done that, and we should have made sure that our list was clean to start with. In other words, the first thing we should have done is show. Having not done that, that's where we got our extra list from. Now, that is a really tricky thing to debug. My guess is it would have taken most people several hours to debug it. So I saved us a little bit of time here. Let's delete item 6. And then show our list again. So right now we have the list that we wanted to have. Now the next thing we decided to do was to start with item E and move it back to the start and then push it back. So we're going to start moving an item up a list, so that's option 4, and we're going to move item 5 up. And let's show. And we can see that it has been moved. Now we're going to move up again, item 4, and show, and it's been moved up. Move up again, item 3, show, looking good. Move up again, item 2, show, whoops, typed in the wrong thing. Now, that may have caused us some problems with our file. Of course, this is one of those errors that we can't deal with at this point. So let's run our program again. But the first thing we want to do definitely is show our list. And notice we've got just one element A in it. So now we're going to add in our other elements. So we're going to enter C after element 2. We're going to add D after element 3. Add E after element 4, and then show our list. So A, B, C, D, E. Now I'll try to do this again without messing up the user interface. So we're going to move an item up a list. And we're going to start with 5, and then we're going to show. Then we're going to move an item up a list, move 4, and then show. So we see E is in fact moving up. Move the item up the list, 3, show, move an item up a list. We're going to move item 2 up and then show. And there we go. We're at the start, and now we're going to move down the list. So move down the list from position 1 and show. Move down the list, position 2 and show. Move down the list, position 3, show. Move down the list, position 4, show. Now we might move down the list from position 5 and just see what happens. Notice, because we tested for that case, we know that it's going to work out okay. So that's great. In fact, we might try some more illegal values. So what if we try moving down item 0? Let's see what happens. Nothing. So that's kind of a nice user interface. One thing we want to remember is that we do have a list that we're going to have at the start of our next run, so we don't have that confusion again. Now let's design our test data for repositioning. Now the first thing we would always do is run all of our other tests again. I'm not going to show that part because it takes too much time, but really it will take you less time to debug properly if you check these things regularly. Then we're going to put A, B, C, D, E in our list. Of course, we already have it there, and because our list is persistent, it will be there. Then we want to move A to position 2 and then back to position 1, and repeat that for positions 3, 4, and 5. The other thing we might want to try is moving A to position 1 when it's already in position 1. While that isn't a very sensible operation, it's not harmful, and so we'd like our software to work for that. The other thing is that nothing should happen if you try to move to position 0 or position 6 on this list. So these are all the little borderline possibilities that we always consider. Next, let's design the signature. Void reposition item, array list of string called list, and scanner keyboard. So we're making the signature of this method match the signatures of the other method in the class. Now, we have to think about how to implement repositioning. So let's take a look at what happens when you reposition 4 to position 1. So in other words, that's putting D at the start of the list. The first thing you would do is remove from the current position. Now, remember our remove method in the array list class takes the elements that are higher up and moves them back into that position. So what we would get when we did that is A, B, C, E. Then we could add to the desired position, moving the other ones out of the way. D, A, B, C, E. And that, in fact, is what the add method does in the ArrayList class. Now, if you didn't remember those details from the ArrayList class, what you would do now is go to the API and look for possibilities. So you might look for a switch possibility or a swap or something like that. Those are fine things to look for. This is just the first way that I thought of doing it, not the only way it could possibly be done. So the add and remove methods in the ArrayList class are just perfect for what we want. So now we're back in Eclipse, and since we're going to be writing code, we will move that down. So here's our move to position method. I've already done the user input. So which item would you like to move and where would you like to move it? The thing that we want to do here, as in the other case, is decrement these so we get them 0 indexed. So source index equals source index minus 1. And destination index equals destination index minus 1. And I'm putting comments in to remind anybody who's reading this code, including you, that that's why we did it. Now, for checking the range, both source and destination need to be between 0 and list.size minus 1. And of course, we need to think about the inclusion here. So if destination index is less than 0 or destination index is greater than list.size minus 1. If you're not remembering where that line of code comes from, this is another use of De Morgan's laws. So I just did it automatically in my head, but we could have done it out loud. And that said, to check that it's in range, destination index would be greater than or equal to 0, and it would be less than list.size. So I just flipped it around automatically. Go back and do De Morgan's laws on paper if this doesn't make sense to you. So this is the case where the destination index doesn't work. So in that case, we can just return. This is the pattern we're using in all the softwares. If they ask you for something that doesn't make sense, we just kind of ignore them. And we want to do the same thing for the source index. So if the source index is less than 0 or the source index is greater than list.size minus 1, we return. So what we know now is that both the source and the destination are in the appropriate range. We do list.remove from the source index and list.add at the destination index. So notice the list class is doing a lot of the hard work for us. Now I wonder why it's not happy about that destination index. Okay, so Eclipse has an interesting point here. The method add takes an integer and a string parameter, not just an integer parameter. So we need to remember how to save the element that was at the source, because if we don't save it, we won't have it to retrieve. So we should do string element equals list.get of source index. So that saves the element that was stored when we do our remove. And now that element can be added there. So Eclipse helped us out remembering something we needed to know. Now that's the only method we need to implement in this part. Let's go and run our program. First thing I'm going to do is show our list so I make sure I know what's in it. Now we're going to take item 1 and we're doing number 6, moving an item to a desired position. And we're going to move item 1 to position 2. And now we can show it. And as we see, item 1 is in position 2. Then we're going to move item 2 back to position 1 and show it. And we will now step through each one of these. So we're going to move item 1 to position 3, and then move, whoops, better show it, make sure it's right, and then move item 3 to position 1. And we have our list back. I'll do position 5 yet, even though you should check the next positions anyways. So 6, we'll move item 1 to position 5. And then we'll move item 5 to position 1. So that's looking good too. And of course, as always, we should be going back and checking that all of our other methods work. Okay, so we remember we have A, B, C, D, E in our list. The next thing we need to do is design the test data for our hashtag case. So we're going to need to insert elements with several hashtags. So here I made a big group, A number 1, B number 2, C that doesn't have any hashtags at all, D number 3, E number 1, F number 1, number 3. So notice F has 2 hashtags. Well, that's kind of interesting. G number 1 and H number 14. And then we're going to need to do retrieves. So some examples, if we retrieve number 1, we should get A number 1, E number 1, F number 1, number 3, and G number 1. If we retrieve hashtag number 2, we should get just B number 2. If we retrieve hashtag number 3, we should get D number 3, F number 1, number 3. And if we retrieve hashtag number 13, we should get nothing. So those are some good possibilities to look at. The method signature should follow our standard design here. Void, find hashtag. We'll have an array list of string called list and a scanner keyboard. Now inside of the method, we're going to need to keep multiple matches. So what we're going to need is a local variable that's an array list of strings that will keep track of everything that's matched so that we can report on it. One thing we might want to consider is what if there are no matches? What are we going to return at that point? Well, we certainly do need to give the user some feedback that there aren't any matches so they don't think our software is broken. So we're going to want to put that in our software too. As far as implementation goes, our strategy will be to step through the array list one element at a time. So that's going to be a while loop. And we're going to need a method for discovering whether a hashtag is in an array list of string. The question is, which class should we be looking at? Should we look at the array list class or should we look at the string class? Well, we're trying to find part of a string. And so that's a string class method, not an array list method. So the string class is where we should go to look. If we went to the API right now, we'd find the same 3 methods that we've been using all along. Starts with, ends with, and contains. A lot of our hashtags were at the end of the line, but not all of them were, particularly in the to hashtag case. So starts with and ends with are not the right methods. Contains looks like our best bet this time. So here we are in Eclipse, ready to implement the search by hashtag function. We've had them enter their hashtag and we've given instructions to include the pound sign and not to use spaces. I got it using next instead of next line. The reason I picked next was I didn't want them to enter multiple words because hashtags have to be contiguous. You can't have spaces in them. The other thing there was I got rid of the garbage by doing keyboard.nextLine. So that cleans out all that other stuff so it doesn't mess up our user input. The next thing we need to do is to check the input. So let's say they enter something that doesn't have a pound sign in it. That's a typical error. If hashtag.contains a pound sign, well, now this is not the trouble case here. The trouble case is when it doesn't contain a pound sign. So then we need to use a logical operator to switch that around. So in this case, I would do system out print line. You do not have a pound sign in your hashtag. So I'm giving the user a little bit of feedback in this case. That's a little inconsistent with what we've done previously, but I think it probably makes sense. We also might want to stop and think whether we really have to do this way. For example, could we have a search function that just looked for anything that was on a list? That might be a really nice thing to do and is an interesting way to expand this program. But for now, let's keep with our original purpose and not get sidetracked. Now we need to perform the search. We were going to create an array list of strings, which I'll call results. Of course, we have to construct it as we always do. Now we're going to loop through, starting with the 0 index, while index is less than list.size. Those are the number of elements in the list. Of course, we're going to want to increment index at the end of the list. So I'm putting that in right now so we don't write another one of those darn infinite loops. So if list.get of index. Now remember, that returns a string. If it makes you uncomfortable to do a lot of operations at once, you can do these things separately. And in fact, I think I'm going to model that this time because it does make it easier for a lot of people to implement. So we'll create a string, which I'm going to call list item. And that's going to equal list.get of index. So then we can say if list item contains hashtag, well, if in fact we have an item that contains the hashtag, then what we want to do is to add it to our results. So it'll be results.add list item. Eclipse is unhappy there because I put in a capital T where there was supposed to be a small one. And I see that I've also forgotten an S on results. And an S on contains. Okay. Now the last thing we want to do is show results. Now there's some cases we want to think about before we do this. One case is what if there are no results? So that's if results.size is 0. Well, in that case, we can say there are no matches for your hashtag. And of course, then we want to return. Now the next thing we're going to want to do is to write out the results if we have them. So int, oh, we already have an index variable. Let's just reuse that one. Index is 0. Now this time we're going to be stepping through the results array, not the list array. While index is less than results.size, we'll do system out println. And we'll take results.get of index. And of course, index equals index plus 1. Okay, let's add our S to results there so Eclipse is happier. So one by one, that will print out the matches. So there we go. We're now ready to try our list. Now, before I get started in this, we had some pretty complicated test data, and it was very thoughtfully designed test data. So let's go to that test data and take a look at it. This is the data that we've been testing. So here's our test data for hashtags. I'm going to move that up on the screen so we can see that while we're running our program. You'll notice that I've been doing this consistently as we've been writing programs, putting in a text file that contains our test data. I think that's a really good strategy because that way you know how the program was tested. And I guess we can move it up just a little bit further to have as much space as possible. Okay, so now we're ready to run our program. Now the first thing I'm going to do is show the list, because we've got a bunch of stuff on that list that we didn't mean to have. Now those things don't really do any harm for us because we're mostly looking at the hashtags, so we could just start adding in our additional elements and that would be okay. So we can add an item. It's going to be A number 1 after item 0. Then we'll add an item and it'll be B number 2 after item 1. I'm going to add an item again, C, and that one was just plain. After item 2, add another item, D number 3, after which item? That's going to be after item 3. Add an item, E number 1, after item 4. Add an item, F number 1, number 3, after item 5. And add an item, G number 1, after item 6. Now let's take a look at what's on our list. And let's check and make sure we got it entered correctly. A number 1, B number 2, C, D number 3, E number 1, F number 1, number 3, G number 1, and then we have these extra A, B, C, D, E's, which aren't going to do us any harm. Now we're going to do our first search. And let's search for number 1. And we see we got A, we got E, we got F, and we got G. And that's exactly what we should have gotten. So that's looking good. Now let's do our search for number 2. And we got B number 2, which is what we were expecting. Now we do our search for number 3. And we got D number 3 and F number 1, number 3. That looks good. Now we do another search for number 13. And it says there are no matches for the hashtag. Well, that really looks great. We might think about whether there are any other cases that we should worry about. Like, what if we had something with a hashtag of 13 and we tried to do a search for 1? So let's add that in. So I'm going to enter A, let's say H, because we don't have an H yet, in number 13. And let's put it right at the start of the list. Okay, now we can do a search for number 1. Uh-oh, we've got a problem. Notice that our H number 13 was found as a match when we were searching for number 1. That's an issue. If you think about it, our number 13 starts with the number 1, and so our contains method isn't finding that. Now, this is one of those things that's going to be a little trickier to solve, because we're going to have to think about how those hashtags match or not. So the reason that 13 was not supposed to match is because it had a 3 where we were expecting a space. So that suggests a possibility for solving this problem. What if we put a space after our hashtag, and then we'll need to match it? So there's a possible solution. Let's go back to our code and implement that. So here's search by hashtag. Here, we're going to put a space on the end. So hashtag, better spell it right though, equals hashtag plus space. Now, this is the kind of thing that can get you into a lot of trouble, so you definitely want to document it. So add on a space so that partial hashtags aren't found. Okay, so let's see what that does. By the way, we really should have quit our program to make sure we get our file saved, because that will save that nice test data that we've worked so hard to build up. So here we're running our program again. First thing we want to do is show our list. So we've got a lot of stuff on the list. Let's see what happens now if we search for number 1. Oh, we find the first number 1, but we don't find any of our others. So we didn't find E, we didn't find G, we didn't find A. Now luckily we also didn't find H, so we did solve the problem that we tried to solve, but we didn't solve all the problems. This is pretty typical in software engineering. It turns out that when you fix an error in code, which is called debugging, the probability of you introducing a new error is about 50%. It's not uncommon to have this happen at all. If we look at our data and think about it, the reason F was found was because we have a space after this. Now with number 1, we had a new line, and so we don't have a space after the number 1, and that's why it wasn't found. So what we need to do is put a space at the end of our original contents in order for this to work. Now let's exit the program so we save our nice test data in the file, and go back to our program and fix this bug. Now we've got to be really careful because we don't want to be adding spaces to the end all the time. We just want to do it while we're doing the search. We take our string list item and we get it from the list. Now let's append a space here. Notice by appending this outside of the list, instead of trying to add it into the list, I'm not damaging our list. It's really important to keep our list pristine. So this is a good way to fix it. Okay, let's run our code and see if things are better now. So the first thing we want to do is show our list so we know what we're dealing with. And let's search for number 1 and see what we get. A, E, F, G. That looks good. And we didn't get H, which is good. So it looks like we got everything there. Now, of course, we should be rerunning every bit of test code we ever have done at this point. So let's do a little bit more. So let's search for number 3. And we get D and F. That looks good. Let's search for number 13. And we get H, number 13. Let's do a search for something that isn't there. Whoops, I meant to type in 31. There are no matches for your hashtag. So it looks like we finally got our program running correctly. The next thing we need to do to improve this program is to improve our error checking. We actually wrote the original version of this program before we knew about the wonders of and or, and so we didn't do any error checking of input, and we really should fix this. So let's go back to our code and do one last fix. So the methods that we have not revisited since we've learned more are add and delete. The read and write file, there's no error checking to happen there. So here's delete item from list. So notice here when the user entered an item number, we just let them enter anything. We need to really think about where that would make sense. If they're deleting an item from a list, let's keep the pattern the same as what we did before. Index equals index minus 1, change to 0 indexed. Now remember, we need to remove the minus 1 there because we've just made a change. And now we can tell what methods would be legal easily. So if index is less than 0, or index is greater than list.size. Now we might want to think a minute, greater than or equal to. If they try to delete something at list.size, we've got a problem because there is no element there because this is 0 indexed. If they try to delete those, we're going to just return. Oh yes, and I see that we called our parameter myList, not list. Doesn't really make any difference, and there's no reason to go back and change that. So let's put in a comment here. If the index is out of range, return. And now we can do the same thing for add. So we enter the name, then we have them enter the item. Now in this case, we didn't make a correction for the list being out of range because we want 0 to be a legal item. If index is less than 0 or index is greater than mylist.size. Now we might want to think again, greater than or equal to. If it's equal to mylist.size, that is not a legal place for them to add an item. Or is it? Well, now wait a minute. We're adding items to the list. So initially they put it at item 0, and that goes into the first position of the list. If they add it after which item, so they would add it after the first item, then that would be just greater than size. So we can see that this case is a little bit different. This is why you have to think through these cases individually instead of just sort of falling into the habit of repeating code that you've written before without thinking about it. So in this case, we'll return. Now this code has gotten a little compact, so let's spread it out. Check the validity of an index. So that's looking good. So now we should have all the error checking our little heart's desire in this program. So let's go back and particularly check those new methods we just added. Although, as I've said time and time again, we should rerun all of our test data at this point. Anytime you change even a single line of code, all of your test data really should be rerun. And I know it's a pain. Okay, so first let's show our list. Now we're going to add, and I'm going to give it a name that's easy to spot, like new item, and add at position 0. So that added new item to the front of the list. Now let's add another new item, and let's add it after position 8. So it's going to add after F number 1, number 3. Another new item after F number 1, number 3. Now let's go and delete those 2 items we just added. 2, delete an item, so that would be item number 9. And we see that that's been deleted. Let's delete item number 1, and that's been deleted. One of the things that's failed in this error checking is I actually haven't checked any of our new code because I haven't made any mistakes of entering the wrong index. So let's check that part. Let's add an item, which I'll call stupid choice, after index -1. Notice that didn't do anything, and let's look at our list, which appears to be undamaged. Now let's add an item too far out on the list. And let's add it after item 27, for example. Well, it didn't break. That's good. And when we show our list, we'll see that it's not there. So that's good too. So this is making a lot of sense. Now we might want to think about how the user is going to feel about that choice. So they told us to add it. They gave us an illegal index, and we just kind of blew them off, and we didn't tell them that that index was illegal. Another choice we could have made here is when they give us an index that's too big to just stick it on the end. That actually might be a nicer thing to do to the user. I'm sorry, not to the user, for the user. We do things for the user, not to the user. So that's a way that you could continue to improve this code. Keep programming.